So in this video, we're going to talk about a very important idea in heat conduction called as steady state, right? Steady state in heat conduction. So it's something that happens naturally when heat flows through a material for long enough time though. So there's a factor of time. So if you let the heat flow, like say you kept a spoon in a boiling water and the other end of the spoon is exposed to atmosphere and all of that. So if you give it 5-10 minutes per se, it will reach a steady state. So what is a steady state? So we have two conditions, 1 and 2, and this diagram to help us reflect on that. Okay, let me actually go to the board and explain the entire thing rather than reading through. So what we have here is a place of heat. So of course, place of energy. So this is at a higher temperature. So this is hot. And at the other end, you have a cold region, cooler region. Say cold. So initially, if I happen to keep a material connecting this, what happens? So initially, the temperature will be whatever the room temperature is. Temperature of the rod is room temperature. You guys agree? So it will start. What will start? It will start heating up. Slowly it will heat up. Slowly it will heat up. And eventually it will heat the entire thing. But after some time, what happens is it will achieve something called a steady state. So my question to you guys is, will it be hot at this point or will it be hot at this point? Which will be hotter eventually. So which will have, say, more temperature. So say this is point A and this is point B. Right. So point A will have more temperature than point B. Do you agree? Point A will have more temperature than point B. So can you imagine that this will have a steady scenario as in this? Same source, same sink. So heat reservoir and cold reservoir. So this is always at 100 degrees Celsius. This is always at 0 degrees Celsius. Connecting that is a rod which is insulated. So through the rod, there is no loss of energy through radiation. This being the case, okay. So this after some time, say this is after time T plus delta T. T naught plus delta T. So this is after a long duration. What happens? You can see these values, they remain same. What values? This temperature values will remain the same. That is, it stops changing with time. It stops changing with time. Okay. So next thing, if I happen to plot, if I take up each value and happen to plot against a temperature distance graph, temperature distance graph, starting from this being 100 degrees Celsius to this being 0, the graph would look like this, guys. So from this point to this point, it would look so. It will be, what is the nature of this? So how does it look like? What is the nature of this? It will be linear. This is a linear graph, is it not? So temperature reduces gradually. And one more thing that I would want to point out is, see, once this is achieved, right? Once you have this particular scenario, once you have steady state. So post steady state, this happens. So post steady state, what we have here is the heat. Whatever heat enters from one end enters the rod. Okay, so whatever heat enters the rod, what do you think happens? Yes, it will exit. The same amount of heat will exit. Same amount of heat will exit the rod. Why? Why not? Or why not? So why being, why is it so? Or why not that this is true? I mean, this has to be happening. See, the thing is, the rod has achieved a steady state. So whatever the temperature it naturally has to reach to, it has reached. So there is no requirement for it to take up any form of energy. That being the case, what happens if you guys are satisfied? You know, you are full. You're sitting in a row, having food, and you guys are full. If the caterer comes asking for extra anything, extra anything, so will you take it? No, right? It'll just pass through. That being the case, it'll just go from one end to another end. Same thing over here. Okay, guys. So this graph is your temperature profile. So it's a profile of the temperature. This is your temperature profile, right? So what we just looked into was something called a steady state heat conduction. See, basically, post a certain point of time, given the source and the sink remains at the same temperature, the heat reservoir and cold reservoir remains in the same temperature. If I keep a rod, this is natural for it to occur, provided it's insulated and all of that, so that heat does not, there's no loss of energy in form of heat through radiation and all of that through the rod. So if this is the setup, by default, within a maybe fraction of time, I can't tell you how much, it depends on quite a few things. So after post some time, it will reach a state wherein whatever heat enters at the one end will exit at the other end. So this is your steady state. So if you look into it deeply, what we look at is the temperature at one end to another end. It will reduce gradually. And so your temperature profile will be linear. Okay, so temperature profile is linear. So this will help you understand this. Okay, so these two are related. Right, so let's read through now. Temperature does not change with time. Every point inside the material has a temperature that stays constant, fixed in time. So dt by T being your temperature, absolute temperature, and this T is your time. dt by dt is 0. For example, for this particular case, left side is at 100 degrees Celsius, right side is at 0 degrees Celsius, and inside 75, 50, and 25. This gradient remains unchanged in time once steady state is reached. Now, temperature can change from place to place. Temperature varies with position, forming a fixed temperature profile. So as you can see, temperature depends on where the point is. If I take a temperature at this point, it will be 75 degrees Celsius. If I take it at this point, it is 25 degrees Celsius, but temperature does not depend on time. It's not a function of time. That's what this expression represents. Right? You have to use a relation function to understand this. So I have a few more things. Physically, what does it mean? At first, when heat begins, temperature everywhere keeps rising or falling. System is unsteady. So as I mentioned, initially the rod will be at room temperature. So what happens to the rod? Eventually, on the right, it will cool down. On the left, it will heat up. So that rod can either heat up or cool down depending on the position, basically. So after some time, the heat energy entering each section per second equals to the heat leaving that section per second. So the temperature distribution freezes. Not temperature distribution freezes, not temperature is freezing. Don't mistake that temperature is freezing. Temperature distribution freezes. That's your steady state, even while heat continues to flow. So heat is not stopping here. So that's an important question. So it can be asked in assertion and reason. So this is a steady state. So what is the consequence? Energy transfer is steady state. So because temperature is fixed at each end, heat current is constant at every cross section. So same thing, whatever I have told. So heat current does not vary with time. So energy transfer is steady. So whatever energy comes from one end, it goes to the other end. There's no loss of energy per se. So mathematically, your temperature profile would look something like this. Temperature will be dependent on time. So temperature at the hottest place minus x times of this temperature gradient will give the temperature or the graph per se. Okay, so let me explain that. So we have basically this equation. Okay, so we are looking at equation for this. So this being x, this being your T of x, the expression for this is equal to T hot. So that's basically this point, TH minus x is this, times of TH minus TL. So this is our TL. So on the temperature graph, this is TL. This entire thing divided by length. So this entire thing is your L. And that's that. Okay, does it make sense? So x and x both are length. Dimensionally, they'll get cancelled. Temperature minus temperature. So all I have to do is, if I have to find, say this is 10 centimeter or something, say this is around 8 centimeter away from the hottest point, the source basically. So if this is 8, what happens? So if I substitute 8 over here, this is 10, this is 100, this is 0. So basically, let me take an example. If L is 10 centimeter, so at x is equal to 8 centimeter, what do we have? T of 8 is equal to 100 degrees Celsius, that is. Then this will be 8 by 10 into 100 minus 0. So as when you solve it, you'll get 80. This is 20 degrees Celsius. So at this point, this will be at 20 degrees Celsius. That's it. So that's what the formula is talking about. So why does it happen? That you guys already understand. So finally, you have your expression. So Fourier's law in steady state looks like this. This we have already seen. Your temperature gradient, area, and your thermal conductivity. So material dependent constant. Okay guys, so that's your steady state. So I think best is you guys can start off with this. So this is time T naught. And this is at time T plus T naught. Sorry, T naught plus delta T. And then the graph, copy the graph. And then the mathematical expression for the graph. Okay, so just have a look at this.